Hello, everyone. Today we are going to talk about a new data structure, binary search tree or BST. From the name, you can understand that this is a special kind of binary tree. And already we know what binary tree is. A binary tree is a data structure uh, to store and manage data, where data is actually stored in nodes, and each node is connected to at most two other nodes, which we call the child. So here in the diagram, you can see a binary tree, right? You can see a structure of a binary tree. You see here is a node, right? This is the root node. It has two child, say left child and right child. Okay. Okay, so what makes a binary tree as a binary search tree? So here is the criteria for the binary tree to be a binary search tree. So suppose we are storing values in binary tree, and say the value for this node is X, this is Y, this is Z. Okay, so for it to be a binary tree, the constraint is like the Y has to be less than X and Z has to be, or Z has to be greater than X. That means at anywhere in the tree, like anywhere in the tree, this should be true. That means even here, say this is A, B, C, right? Even here, A has to be A has to be greater than B, and C has to be greater than C. C has to be greater than A. So in short, I can say that the left child is going to be smaller than the root, and the right child is going to be larger than the root. Okay. In cases like if the binary search tree has values, duplicate values, we can modify this rule a bit, where the equal values actually go to either right side or left side. Okay, but not both, like on either of the sides. Okay, so this is the condition for binary search tree. Next thing is, say we know what is the, so this is, suppose this is the left subtree, right? So anything in the left subtree has to be smaller than X. Anything in the left subtree has to be smaller than X. And this is the right subtree, right? So anything here is going to be greater than X. So that is the condition for binary tree. Let's fill this up with values, and so that it looks like a, so say this is 50. Let's make it say 10. This is 20. Say this is 5. Yeah, on the right subtree we have bigger values, so 60, and then we have say 55. Okay, and then we have say, okay, here is the thing, we cannot actually put 49 here. Why? 49 is actually less than 55, right? But we cannot do that because everything here has to be less than 50, right? Sorry, greater than 50. So it cannot be 49. So any other value, say 50, 52, okay, and 57. If I wanted to put 49, 49 would have been, say I want to add another value, 49. Where do I go? Obviously, I have to come this way, and you see 49 first comes this way because it's less than 50. Then it's greater than 10, so it comes this way, right? And then it's greater than 20. That means 49 will go here. Okay. Okay, so there goes the binary definition of binary search tree. Now let's talk about a problem. As you see, let's focus on this thing, search. So it looks like the binary search tree is going to help us doing search in smarter ways. So before going into details, let's talk about some of the existing data structures. Okay, so let's talk about, we say this is the search problem, right? So the search problem. So some of the existing data structures that we have are like linear data structures, array, right? Let's make an outline for an array. So we know that array is of fixed size. Array has index. And then we have like linked list, another data structure. We know linked list has nodes which carry values and also has a link to the next node. Okay, so this is okay. So for the array, we know, suppose let's put some values in the array. So let's say insert operation on an array. So this is say 20, 6, 9, 60, and 10. Okay, so you can see that every time I am adding a new value to the end, so the insert is order of 1, right? Every time I am just adding to the next, to the next index. Delete is going to be a little bit, it might be a little bit challenging. So suppose if I delete 9, in that case, what I have to do is, we know the elements of an array, actually, they are actually kept together. So we have to shift 60 here and 10 here, right? We have to do shift. So if I had deleted the first element, say 20, I had to shift everything, right? Shift everything to the left. So in that case, we can say deletion can be order of n. Now the important one that we wanted to talk about, the search. Okay, so search, someone says like, do a search of, say, search for 15, right? In that case, to come to a decision that 15 is in the array or not, we have to check everything, right? We have to check everything here. And then after checking everything, only then we can say that 15 is not here, right? So that means for search, in the worst case, we have to search everything because this is an unordered array. Unordered array. We don't know which value is where. So we have to look for everything to do a search. Okay, so let's talk about the linked list. So in the linked list, suppose already there are some values here, 6, 60. Now let's add another value, insert 10. For the linked list, we know that there are 2 pointers. One is head pointer, and the other one is the tail pointer. This is the tail pointer, right? So when we actually insert a new value, we insert in the tail. So we're going to insert 10 here, sorry. And the new tail is going to be here, right? So this is going to be the new tail. The insert is at the tail, that's fine. We can just directly go there and do the insert. But the deletion can be challenging. So say someone says like, delete, say delete 10 or delete 60, right? In that case, what's going to happen is I cannot just, this is not a random access data structure like array. In array, we knew the index, we could just jump there and do something, right? I cannot just jump in here. I don't know where 60 is. I have to start from the head and then move on and see where 60 is and then do the thing there, right? So in that case, I may need to like go through the whole linked list to find my element and do the deletion. So going like just iterating through or iterating through that linked list may take order of n. Search is again order of n. As you can see, even before deletion, you have to search for it, right? So you have to start from the head. You have to start from the head and then start going through the nodes to search, right? Okay, search is order of n. That is for linked list. Now, as we said, like we always want, suppose we want to do search more efficient, because in the data structures we are storing values, and obviously we want to do search, and we may need to know what values are in there. So search is a very important operation. Now let's think about this. Can we think like if my array was ordered, somehow it was ordered, say 1 10 sorry 1 6 10 20 60. If somehow my array was ordered, in that case, if someone said like search search for say 2, right? Search for 2. What I could do is, I know that the size of the array is 5. So I could just, instead of just trying from the beginning, I could just jump to the middle. We know for the array, we know every index, right? So we could just jump to the middle and see if we could just jump here and then check if 2 is greater than or less than this value 10. We see that 2 is less than 10. That means we can just immediately say that there is no chance that 2 is in this range, right? So the new range for 2 is going to be this. Can you see that? Okay. So we keep on doing this until we reach just like everything is exhausted. So this is binary search. Already we have talked about binary search in the previous videos and lectures, right? So the thing is, we are reducing the search space by half every time. So if there are like k steps before we, if we say like if there are k steps before I come to the decision, can we say that if there were initially like n numbers, and every time I was dividing the search space by 2 until the search space becomes 1, right? So we can say that k equals to log 2 based n. In that case, so if it's ordered array, then the search becomes much more faster, log n, right? But there is it has its own challenges. So the challenge, let's look at the challenge here. So let's say I want to insert, say here in this array, I want to do an insertion. Say insert okay, just for now, let's assume that there was another space in the array, still it's empty, but I want to insert say 2, right? And I can find that 2 belongs here, right? 2 belongs here. So I have to start from the beginning to see where 2 belongs. That itself takes order of n. Not only that, I may have to shift everything, right? Shift everything to the right. That also takes order of n. So order of n plus order of n. So the insert becomes order of n. Again, deletion, the same thing like an unordered array. You delete something from the beginning or in the middle. You have to shift everything to the left. So you can see that although the search becomes very much more faster, we have a costlier insert. So that's an ordered array. So let's look at, say, the binary search tree. how the binary search tree can help in this case. Okay. So binary search tree can actually do amazing things. Insert may become order of log n. Delete may become order of log n. That's 2 based n, okay? And search also may become order of log 2n. How this is possible? This is possible, sorry. This is possible if you have, suppose this, right? And then say something like this. Say you are looking for something, so this is say 50. Then you are looking for 60 in this tree. Search 60. So immediately you know that. So you start from the root and you are searching for 60. And you see 60 is greater than 50, right? 60 is greater than 50. So we can immediately say that I can just remove this portion. I don't need this portion anymore. So can we see that half of your search space, initially your search space was n. In the next step, your search space dramatically becomes n over 2, right? So we are done with this. Next time, I just have this portion. I just have this portion left for my search space. So suppose this one was, say this was 55, right? You can see that 60 is still greater than 55. So can I say that in the next step, this portion is also gone? So I don't have to search it here, right? Because there is no chance that, because everything in the left is even smaller than 55. So now from n over 2, my search space now becomes n over 2 squared, that is 4. So I keep on doing this until I reach 1, which is actually after k steps. So after k steps, if I am here, n over 2 to the power k, which is 1, then I can come to my decision, right? So this is k then becomes log 2n. So there goes my search. Now, the other things, let's talk about the other ones. Insert. So suppose I want to insert, say, 10, right? So if I want to insert 10, then first I check again as the root, and I see that 10 is smaller than 50. So can I immediately just remove this portion? There is no chance 10 is going here, right? So 10 will be somewhere here, will go here. So even for insert, I am just reducing my space by half every time. So insert also becomes the order of log n. Similar thing is for delete. If I want to delete, say you want to delete something, say you want to delete 50, sorry, delete say 20, then you search for 20 here. You see 20 is less than 50. Now you know that this is gone. So this part, there is no chance 20 is on the left. You have to check it on the, sorry, 20, there is no chance 20 is in the right. You have to check on the left. So insert, delete, and search all becomes order of log n. So here is the one thing. This is only true if this is only true if the tree is balanced. So what is a balanced tree? Okay, so the definition of a balanced tree is at any node, uh, difference of height of right subtree, so right subtree height and left subtree height the difference is maximum 1, is less than equals to 1 at any node. The difference of the left subtree and the right subtree is 1. So let me show you. So this subtree was suppose balanced. I'm going to show you how this was balanced. So this was balanced. The reason for that is, say if you come here, right? Left subtree height is 1, right subtree height is 1. Okay. So the difference is 0. Let's check here. The right subtree height is 1, 2, right? Left subtree height is also 2. So this is also, so everywhere you can see the different right subtree and left subtree has the same thing. So here, let's see here. Here, if you check here, left subtree height is 0, right subtree height is 1. Difference is 1, which is less than equals to 1. That is fine. If I come here, right? Right subtree height is 2, left subtree height is 1. So difference is 1. That's the maximum difference allowed. Now, if you check here, right subtree height is 1, 2, 3. Left subtree height is 2. Okay. Okay. So it still is 1. But if I have like more, say this. Now see. Now it's no longer balanced. Because here, if you come here, what is the left subtree height? 0. What is the right subtree height? 1, 2. So the difference becomes 0 and 2, 2. So this is no longer balanced. So you can see that if it's balanced, then there is always the similar number of nodes on the left as well as the right. Okay. But if it's imbalanced, then you see obviously from this one, like the example here that you can see, it is imbalanced now, right? So it has more nodes here than here. So what happens is, once you are actually reducing your search space, right? If you just reduce your search space, you are not reducing necessarily by 2. You are sometimes reducing by less, right? So we cannot guarantee that if it's not balanced, then it's going to be order of log n. Now there are techniques to keep the binary search tree balanced. We'll talk about those techniques later. And obviously your next question might be, if it's not balanced, then what happens? What is the complexity of insert, delete, and search? Okay, so let's look at this binary search tree. So this is say 10, then 15, 18, 20. So you see every time the new value is getting inserted to the right. So this is a linear kind of thing. So this is a totally unbalanced binary search tree. So next time if I want to insert 40, what do I have to do? I have to first check here, right? And it says, okay, go to my right because you are bigger than me. This one also says, go to my right. This one also says the same, right? And finally I get and add 40 here. So insert becomes now order of n, right? Similarly, search becomes order of n, because I may have to go all the way down to search for something, right? I cannot even reduce my search space by half. Suppose someone says, look for 60, search for 60. So this is an imbalanced binary search tree, although this is a binary search tree, but this is so imbalanced. So for 60, I go here, it says, okay, search to my right. This also says the same. 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 Finally, I know that 60 is not there, but by then I already have checked all order of n. So in the worst case, the search is also order of n. Delete is also order of n. So this is if your binary search tree is not balanced. So binary search tree is a wonderful data structure to store data where the search, insert, and delete everything becomes so fast. But the thing is, the trick is you have to keep the binary search tree balanced, right? Okay, so that's it for today. We'll come back with another topic for the next lecture. Thanks for watching.